Hello everyone, welcome to Dr. Ravi's Academy. In today's virtual class, you will be solving a problem on bending stress. And as you know, in previous video lecture, we have derived the bending equation and using that bending equation, we will be solving this particular problem. Let us look at the problem. A simply supported beam, that is SSB, having a width of 200 mm width and 300 mm depth, and it is the length is 4 meter, that is 4000 mm long, and of course it is shown in figure. He is asking you to find out to determine the bending stress at point C. So this point C is located at a distance 1.2 meters from the left support, and the bending stress required is, the point is such that it is 60 mm from the top. So it is below the top surface by 60 mm, and is asking what is the bending stress of this particular rectangular beam. So this particular problem we will be solving by using bending equation. Let us write down, first of all let us write down the bending equation, that is m by I is equals to sigma by y is equals to E by rho. If you look at the terms involved in this, m is bending stress, it is bending moment. Let me write, it is a bending moment, the terms involved in this, and I is the centroidal area moment of inertia, it is MOI, about the centroid of the cross section, and sigma is the bending stress, it is a bending stress at a given point. He is asking the stress at a particular point, that is point C, and y is the distance from the neutral axis, it is the distance from neutral axis NA. Of course, these two terms, A is Young's modulus, it is modulus of elasticity, and rho is the radius of curvature. These are the the terms involved in this bending equation. So using this particular equation, you will be solving the problem, and we will be using first two terms of this equation. So to calculate the bending stress at a given point, you need to calculate bending moment at a given section at point C, and moment of inertia of the cross section of the beam, and y is the distance of this particular point from the neutral axis. From the neutral axis you will be measuring. So these are the various parameters you are supposed to solve, and to solve this problem, first of all let us find out the support reactions, that is RA and RB. To write this bending moment, you need to find out the support reactions. Let us look at this. The total load is 200 kilonewton per meter, that is into 400. So let us write down sigma MA is equals to 0. Treat anticlockwise moments are positive, and see that it is RB. Your RB, it is contributing anticlockwise, which is positive. So I am writing this as RB into the moment arm 4 meters, and the load contributing clockwise turning effect, that is minus 200, and length is 4, and it is acting at a distance of 2 meters, is equals to 0. So from this you can solve for RB is equals to, it is 200 into 8 by 4, this becomes 400 kilonewtons. Your RB is 400 kilonewtons, and total load is 2 into 200 into 4, that is 800. So obviously your RA is also 400 kilonewtons. The very first step of the problem is you have to find out the support reactions. After finding out the support reactions RA and RB, write down the bending moment at a distance, this you call it as x. I am calling it as mx is equals to RA, which is contributing sagging effect, which is positive bending moment, and as per your WhatsApp symbol you can call it as smile effect. Smile effect is positive, and writing it as 400 into x. So this is the moment arm, that is x is it here, it is of course it is given, you can write down 1.2. It is 400 into 1.2 contributing sagging effect positive minus, so this load 200. So you can write down 200 into, this length is 1.2 becomes a load, and moment becomes half of this 1.2 by 2. So this is the value. So you can write down this as it is 8. It is this value you are going to get. It is a bending moment as 336 kilo Newton meters. So mx value you are going to get 336 kilo Newton meters, and this is one of the value required in your bending equation. The first value. I is the moment of inertia, centroidal moment of inertia. So let us draw the magnified view of this particular section. I am writing it as the magnified view. This is 200. So this dimension is 300. Neutral axis, this is exactly half of that. It is 150, and the point C is given from the top at a distance. This point C is 60. So from neutral axis, this distance becomes 150 minus 60, this is 90. So your y value will be 90. So y is equals to 90 mm, right? And your I value, so you have to calculate I value. I is equals to the moment of inertia of the central moment of inertia. It is B, it is h cube by 12. B is 200 into h is total depth, that is 300 cube by 12, and this value if you calculate you are going to get, it is 450 into 10 to the power 6 mm to the power 4, it is in millimeters. So you got m value, that is 336 kilonewton meters. This is equal to, you can write down, it is 336 into 10 to the power 6, it is Newton mm. So there is a consistency in unit, that is force are in newtons and distance are in mms. So y is 90 mm, and I value got, it is 450 into 10 to the power 6, and the only left out term is your sigma. So sigma is equals to, the bending stress sigma is equals to, it is m by I into y. So here substitute all the values. You have m value, that is 336 into 10 to the power 6, it is Newton mm, divided by, it is 450 into 10 to the power 6 into y value is 90 mm. That y value you are measuring from the neutral axis, because your bending equation, this value is always from neutral axis, and if you calculate this, you are going to get, it is 67.2 Newton per mm square, that is bending stress. And of course this is also, you can write down, it is sigma is 67.2, it is megapascals. This is the answer. Thank you very much for watching this video.